All right, time for another DraftPhysics.com, debatephysics.com also. But as stated, debate is lousy. So this is the fourth video in a series on classic physics is what they call it, but it's not physics they believe in, and it's physics they've perverted. It's not really Newton's physics. They imply it's Newton's physics. It's not Newton's physics. It's not Galileo's physics, not Descartes' physics. It's Huygens and Leibniz, and they really don't want to just admit that for some reason. Because it's wrong physics is what it is. Plainly, easily demonstrated. So, let's go to... We have some comments, okay, useless, crappy, stupid comments, but, you know, not much you can do. So this blobby guy makes another sock account so he can do the same thing over and over again, which is insist that somehow I go over all of their silly mathematical derivations. I don't have any obligation to do that. I'm arguing, look, you can just be a rational person. You say, is it 9.8 meters per 1 second or not? If you believe something else, I'm saying you're a lying sack of shit because it's quite obvious that it's a time-dependent force. It's measured in units of time, seconds, single 1 second units, not seconds squared. It's not 1 seconds squared. All right. That's not a rational definition of reality. All right, so he says, how much do I need to pay you to explain where exactly the unit meter per second squared gives the wrong result? It's every single circumstance in which you're taking a 9.8 meters per 1 second and changing it into some sort of thing like, well, it was 5 seconds and 5 squared is 25. That kind of thing, moron. Are you a coward? You know, well, fuck you. I mean, you know, again, they think physics is this moronic math, and I've pointed out how MGH doesn't work. So if an object already has velocity, you can't use MGH because it doesn't give you the right answer, because it doesn't really understand what gravity is, which is a time-dependent force. It happens in units of time. It's 9.8 meters per second of velocity per 1 second. And it's 9.8 meters per 1 second per 1 second. You can't square a 1. Fuckhead. All right. And the irony is this other asshole shows exactly what the problem is. Shows exactly why they pervert this nonsense of per second, which nobody says. Nobody says 60 miles per hour. Of course, every hour per hour. No one says 60 miles an hour per hour. Okay. Velocity and time. Velocity is measured in meters per second. Fuck you in the ass. Oh, goddamn. Like we already know that. Indicating how much distance the object covers in a specific amount. Yes, 1 fucking second. We know that the unit would be useless if the unit meant any number of seconds. Obviously, the unit designation has to be in standard units of 1 unit. It's 1 meter, and it's 1 second. All right, change in velocity. Acceleration refers to the change in velocity. Well, fuck you. God damn. It tells you how much velocity changed in each second. Yes, we know all of that, fuckhead. All right, then he says unit explanation. If you have a change in velocity per second and the velocity itself is in meters per second, then acceleration equals change in velocity divided by time. So we know the velocity already has a time unit in it. It's already 60 miles per hour or whatever it's going to be. And you're putting it under another piece of time. You're saying it's a time unit. No, it's just a unit. And it's 1 unit of time. 1 second. Okay? It's 60 single miles per 1 single hour. All right. Units of acceleration, meters per second divided by seconds equals meters per second squared. So we just did it. He's just showing the other asshole this is exactly what they do. Per second means that I square the seconds. No, you don't. It's only 9.8 meters per 1 second. That's all it is. 9.8 meters per 1 second per 1 second. Okay, so you get 9.8 meters of increase in your velocity, 9.8 meters per 1 second. Oh, Jesus, you're just playing. I mean, it's insipid to have to play word games like this. Again, nobody says 60 miles per hour per hour. Nobody on earth ever says that because it's stupid and redundant. All right, so acceleration is meters per second, so it isn't, because it shows how much the velocity in meters per second changes each second. And it doesn't change any squared seconds. Again, 1 times 1 is 1. You cheaters, you're just such gross cheaters. Think of it like this. If you were a car and every second your speed increases by 5 meters per second, so you're falling in gravity, right? It's a better example because cars don't really work this way. Constant acceleration is really hard to do. But anyway, you're falling in gravity. The first second, you gain 9.8 meters of velocity, 9.8 meters per second of velocity. That's all you get. The second one, you drop another second. You go 3 times the distance, but you only get another 9.8 meters per second of velocity. You aren't gaining 4 units of energy. You aren't squaring anything. All right, your acceleration 5 meters per second squared. So here he says it again. Does not make sense. Does this make sense? Of course it doesn't make sense. Squared seconds. What second? What does that S represent? It represents 1 second. That's the unit you're using. You're not using 10 seconds or 15 seconds or any number of seconds. It's divided by 1 second. Are you denying that it's 1 second? It's 9.8 meters per 1 second. Not 5 seconds, not 15 seconds, not any number of seconds. It's 1 fucking second. You fucking cunt. All right, so I'll just delete this, but fuck you. God, what crap. I don't want to report anything, you fucker. I just want to delete the fucking thing. I said remove, didn't I? Yeah, I guess my mouse was in the wrong place. Alright, so fuck. God, people just suck. These other commenters laughing my ass off. And then good points, which isn't saying much, but whatever. God damn it. I'm just surprised people can't do a little better than that. Alright, I gotta use my mouse to get rid of this shit. Alright, so I don't need to draw anything yet, I guess. We'll play some video and then I'll get to it. Alright, gotta fix the volume. Sorry about that. And such. Alright, so this is a video called Position, Velocity, Acceleration Part 2. Graphical analysis. How exciting. Alright.
Hey, it's Professor Dave. Let's do some graphical analysis.
He knows a lot about the science stuff. Professor Dave explains.
So he really doesn't know much. Okay, he doesn't know the history of Huygens, Leibniz, de Chardolay, and then it's not really Lord Kelvin's fault or Joules' fault. I mean, they all just fell into this stupid thing that somehow somebody had proven it somewhere. And they didn't bother thinking about it and saying, well, you know, it doesn't make any sense, really, because I never saw anything. I never saw it taking 25 times the fuel to move something 5 times as fast. So that does sound like shit. All right, back. Should be anyway. I hope. So, yeah, might as well draw it. Okay, so during this so many times, and there's just no, I don't think a reasonable person can debate this. I mean, it's just so simple and factual, and, you know, it's Galileo proved it and demonstrated it anyway, asserted it, and, you know, did a big pile of experiments to prove it. So you drop something in gravity, and so what you're really doing is just saying, okay, it could be a stream, you know, of something, it could be wind, it could be lots of different things that are causing the motion. This happens to be a force that's moving the speed of light, so it's a force of almost infinite speed compared to the speed that the object's actually going to move. So there's no like a boat, you can catch up. Like the wind can be 30 miles an hour, and your boat can go 30 miles an hour. You can go as fast as the wind. But this wind you can never go as fast as, so it's always going to accelerate you. And because it's moving so much faster, it's going to accelerate you at the same rate. Now, if it were possible for you to fall a very long distance and gain a really great deal of speed, the fact is maybe you could go half the speed of light, and then the force will only be 4.9 meters per second, because you're going almost as fast as, right? As you're going faster and faster, it gets harder for that force to push you faster and faster, because less of it's going as fast as you are. You're going as fast as. All right, so less of it's going to impact you. Okay, but the simple truth is, in the first second, one piece is 1 unit of time, 1 second, okay? It's not any number of seconds, it's 1 second. You travel 4.9 meters, all right? And you'll now have a velocity, okay, that equals 9.8 meters per 1 second, okay? If we say meters per second, you don't say meters per seconds. All right, it's not going 9.8 meters per second squared. Yes, that's per seconds. All right. And so now that you have that 9.8 meters, you know, well, so now this is what the force gave you. The force acted on you. The force impacted you in its 1 second unit. It gave you the appropriate amount of velocity. Now what's going to happen? Well, without the force, you can understand that you're going to get 2 more units of 4.9. That is, you're going to get a unit of 9.8. So in the next second, you're not going to need the force to push you to go these 2 units. You're going to get those 2 for free. Okay, those 2 4.9s. And what's the force going to give you in the second? That's right, it's going to give you 1 more unit of 4.9. And that's all. So you're going to get a 4.9 added in terms of distance by the new force. Okay, this distance is all without a force. You don't need any force here. The unforce causes this. Okay, the force causes this, and you're going to get a plus 9.8 meters per second increase in your velocity, and now you're going to be going 19.6 meters per 1 second, not second squared. So clearly, time-dependent force. This is 1 second. All right, this was 1 second. You got 3 units of distance here. You got 1 unit of distance here. And if you keep going, you'll get 5 units of distance the next time, and then you'll get 7 units of distance. Again, this is all what Galileo did 400 years ago. There's nothing in here. There's just 2 units of time. The 2 units, you got your 2 units of velocity. Where's there any reason to think you got 4 times the energy? You've only got twice the speed. You're only going to weigh twice as much, by the way. Okay, well, that's an experiment your physics hasn't done. Okay, but I have, and that's how it works out. So you got twice the weight, twice the speed, twice the time, and yet you think there's 4 times the energy. And I'm saying it's kind of obvious that it's nonsense. It's not true. It's not true. Yeah, that's as simple as that. It's not true. All right. So, back to the crap and such. Just a mess here.
One of the best ways to do quantitative analysis is to make graphs.
I gotta do an edit to the video because really the first video was just graphing. It was too simple and too non-controversial, so forget it. So this kinematics, when he starts that, this is a little bit more interesting, so we'll play with this instead.
Motion of all objects, whether on Earth or in space. It is simply that on Earth we must make approximations, since there are a greater number of variables, like friction and atmosphere, that affect motion in various ways.
Right, and they don't really pay attention to those variables. So as found out with like spring experiments, they don't really talk about the fact that springs don't give back everything they're given. So they collect energy really well. They don't give it back so well, because the faster they release something, the more likely it is they're still going to wobble back and forth, indicating they didn't give away all the energy they had. So there's lots of little things you got to be careful about with experiments. And the truth is that MV will never steer you wrong, generally speaking. So all of this is controlled by mass and velocity. It's weight, it's thrust, it's energy, it's work, it's everything. Heat, it's all MV. It's all just little masses or big masses moving a velocity.
The kinematic equations include variables for displacement, velocity, acceleration, and time.
So it's just confusing, this whole distance and displacement thing, because they acknowledge, they call x distance, and so it just confuses things. And then they use t for, well, anyway.
And in the context of kinematics, acceleration will always have a constant value.
So it really doesn't. So in the real world, there isn't such a thing, except for cases like gravity. Certain specific cases, but in all the examples they use, the acceleration will never be what they claim it to be, because it won't be constant. It's very hard to constantly accelerate in a car. It's like impossible, because the speed of the engine, your car catches up to that speed, and you have to add more acceleration, and there's no way you could just accidentally. I mean, you could accidentally, but I just mean it's really hard to do it on purpose, to accelerate at a constant rate. Really hard to do.
Whether positive, negative, or zero, since we won't look at forces that could cause acceleration to change over time.
Well, of course it does. So his example is going to be a perfect example of something that doesn't accelerate constantly.
When you see a subscript of 0 after velocity or displacement, it indicates initial.
So final velocity is Vt or Vf. So I don't know why exactly Vt would be final velocity, but that's how they're writing it. Not my fault. So it's another. I'd call that a bit of an imbecility, frankly.
Conditions, which will have some implication depending.
So d or x. So the distance is d or x.
Depending on the problem we are looking at. Here are the three fundamental kinematic equations we will be using.
So the first one's pretty easy, okay? So there's no argument there. If your acceleration is 9.8 meters per second and you just multiply it by some number of seconds, and you're not going to square the time or do any of that horseshit, you're just going to do a simple 9.8 times. No issue.
The first one says that the velocity of an object at any time t is equal to the initial velocity plus the acceleration times time.
So you could just say the acceleration period, because you could just say the net acceleration. So you could do the math ahead of time. If it was, if you accelerate for 2 seconds, you could just do it ahead of time and say, okay, it's 19 point, in gravity it'd be 19.6 meters per second. You could just say what was the net acceleration. So I'm just saying they could get rid of the AT and just put net acceleration.
The next one says that the position of an object with respect to a point of origin will be equal to its initial position plus the initial velocity times time plus.
So this one is this 1/2 AT squared is really just the gravitational formula showing up again. So I don't know if I want to redraw it, but I could redraw it. I'll wait till he does his example. But really what all you're saying is the acceleration is 9.8 meters per second, but we know when you're constantly accelerating, that is a very constant rate, you're only going to travel 4.9 meters in that first unit of time. So that's why the 1/2 is there, because it's basically saying 1/2 the 9.8. If this was a gravitational formula, you'd just be saying 1/2 of 9.8 is 4.9. And now you're going to say, okay, because it's half the unit of distance, you're recognizing that, yes, the time is going to be quadratically related to the distance because you're going to gain velocity, and the velocity won't require any new force. Okay, so all of that extra speed will just be accrued, and that's why the t is squared. So it's just acknowledging that in 2 seconds you go 4 units of 4.9, 2 units of 9.8. It's that obvious.
1/2 the acceleration times time squared. Lastly, this one says that velocity squared is equal to the initial velocity squared plus twice the acceleration times the displacement.
So it's kind of just a way of rewriting that the one above it, but anyway.
Other supplemental equations include these two, which are easily derived from simple definitions, which state that position is equal to the average velocity times the time interval, and that the average velocity is equal to final velocity plus initial velocity over 2, which is the definition for any average.
Right. So those are non-controversial.
Now that we have these equations and know what all the variables mean, we are ready to apply them to real examples of motion.
So it's not going to be a real example. It's going to be a contrived, idealization.
Say you get an
Well, which is fine, but just make sure you're pointing it out that it's really, you're just duplicating a gravity scenario, except now you're going to do it in a linear way and pretend friction and air resistance and all these other things don't matter. And so basically you're just going to say this car is falling at a rate of 2.5 meters per second. And then it's going to fall for 10 seconds. So it's just this, it's just redoing the idea that you're adding a constant force when nobody can accelerate at a constant force.
in your car to drive to the supermarket. While at rest, you place your foot on the gas and apply a constant acceleration of 2.5 meters per second squared.
Right, so that won't happen, and it won't be per second squared. So it's just like the 9.8 thing. There's no reason for that squared second. It shouldn't be there. It doesn't say anything. It's like saying 60 miles per hour per hour. You wouldn't do it, and you certainly wouldn't multiply the hours times the hours. So it's just a nonsense.
Squared. What will your velocity be after 10 seconds, and how far will you have traveled in that time?
So your velocity after the 10 seconds is going to be easy because that's just adding 2.5, and then it was the next second was 2.5. So just like the gravity argument. So maybe I'll just draw that. Just to I mean, it's, I've been over this so many times. I mean, it's just, it's almost like, okay, it's terribly redundant. But that's sort of what's required, I guess. So really, we've just taken the gravity argument and put it on a road now. So this could just be falling down, and you're just saying, what's the falling force? And you're saying it's 2.5. And so you're saying, well, what's the units of time this time, right? So in the 2.5 acceleration, you only got 1.25, of distance. So they're just 1.25 units of distance, 1.25 units of distance added, but you're getting the velocity for free. So you get the 2.5. Yeah, it doesn't erase very well. I have to get some better tools here. Anyway, oh, you can't really see that. My bad again. I really should be able to get this right. All right, just redraw it, Gary. Yeah, fuck it. Yeah, that's the solution. Didn't draw it very well anyway. Didn't really mean to be way up here. All right, so the idea is, all right, it's going to be 2.5 meters of acceleration. So as before, you have to work for the first one. These two you're going to get for free. Okay. Then you're going to add this one in the next unit of time. So this is 1 unit of time. And then you got 1 unit of time. And then you're going to get 3 units for free here, because now you've increased your velocity. 3 units or 4? well, whatever. I'll work on that. And, you know, it's just going to keep going that way where you're going to keep, it would be 3, so it would be over here. And so you're just going to keep gaining this velocity. So the amount of distance you're traveling per second keeps increasing as your velocity increases. And it's this quadratic relationship between the units of time and the number of these units of distance. And that's all you need to know. So again, it's Galileo figured this out. You know, it's 1, 3, 5, 7, 9, all the odd numbers. 1, 3, 5, 7, 9, you know. All right. So that's how much distance you get per second for each second. So you gain those 3 in the second. The third second you get 5 units of distance. The fourth second 7 units of distance. 9 units of distance. So that's the relationship that exists. And these just add up to the squares. Okay, continuing. So he's just taken a gravity question and he's turned it into a road question, but it's under this false circumstance that you could actually accelerate your car where, you know, every second you just went 5 miles per hour faster, which isn't that easy to do.
We can use these two equations to find the answers. We just have to plug in what we know. For the velocity, we know that the initial velocity was 0 because we were at rest. So we just multiply acceleration by time and we get 25 meters per second. That is the velocity of the car after 10 seconds. Now to find how far...
Right, so pretty uncontroversial. But the distance you moved in each second is increasing quadratically.
You will have traveled, you will use this equation. Once again, initial velocity is 0, so this entire term can be ignored.
Right, so all you have is half the acceleration, which is the distance you traveled. So the half the acceleration really is just saying you only went 1.25 meters. That's the only distance you get from your acceleration. So your acceleration only produces 1.25 meters of actual distance. And that's all you add each second to your velocity is, to your total distance, is that extra bit. And the rest of it's all dependent on your accrued higher and higher velocity.
Then we have 1/2 times the acceleration times 10 seconds squared. And we should get 125 meters traveled over this time span. So it really is this simple. You just choose the equation that is appropriate for what you are solving for and plug in what you know.
And again, what you know is that most of the velocity, the distance, is the velocity you created that you're not losing because there's nothing stopping. So there's no air resistance in this circumstance, nothing to stop you from losing any velocity. So it's free fall without any terminal velocity.
Let's now consider a car that is already in motion with a velocity of 27 meters per second. Let's say you need to stop suddenly, so you press on the brakes.
All right, and so again, this part's really gonna, you really have to know what the surface is capable of doing. But anyway, he says the deceleration is 8.4 meters per second. And again, why is it squared? Who the hell knows? Okay, it's no good reason for it to be squared.
Creating a rapid deceleration of negative 8.4 meters per second squared.
And for how long did you do that? I don't know.
How long will it take the car to come to a stop? And how far will it travel while your foot is on the brake?
So he's basically saying that your deceleration, okay, your minus acceleration, is again constant and it's happening per second. So obviously you're going to run out of, the 27 in 4 units of the 8.4, right? Something like 4. 16, yeah, it's a little too much. So 3 something units of time. So in 3 seconds, 3+ seconds, you'll have wiped out your initial velocity.
Once again, let's use this equation to solve for time. It must be this equation because we know everything in it except for time. For velocity, let's plug in 0 because we are curious about the time elapsed at the moment that the car stops moving.
So that's kind of weird just because, you know, well, whatever.
And the velocity, when it has stopped moving, will be 0. The initial velocity is the 27 meters per second we mentioned, and we can plug in the acceleration, solve for time, and get 3.2 seconds.
Right, so just what I said pretty much. And so he's assuming a constant deceleration, which again isn't possible. It really isn't possible to constantly decelerate.
Now,
Especially when the friction gets stronger and stronger, the slower you're going, you know, the wheels bite more, the whole thing changes, so you're decelerating a lot more as you start going slower.
now that we know the time associated with this event, we can use this other equation to find the braking distance. We plug in the initial velocity and
So it's the same scenario, you're just doing the same basic thing of saying the distance is the deceleration has the same rules, okay, where you know you might be decelerating at 8.4, but you're only going to travel 4.2.
acceleration we mentioned before, as well as the 3.2 seconds we just calculated, and solve for x, which will be about 43 meters traveled from the moment you applied the brakes to the moment that the car stops moving.
Right, and that's only under this bizarre circumstance where you can actually manufacture some kind of constant deceleration.
These equations work for any other object just as they do for cars.
That's right, so they don't really work for any other object because the variables aren't ever ideal, and as there's not too many forces that you can apply like gravity that are going to be constant, and constant at an almost infinite speed. So again, the catch is you can make some argument about wind, but again, wind, you can catch up to how fast the wind's blowing, and it gets harder and harder for the wind to push you faster the closer you are to the speed of the wind itself. So
let's check comprehension.
So we won't bother doing that, of course. Yeah, fuck that. And such. Let's see if he said anything else. It won't be anything else but subscribe, and I have to make more videos, so, you know, subscribe.
Patreon so I can keep making content. And as always, feel free to email me, Professor.
Yeah, no point. Yeah, I tried that. I'll try it again. What the hell? Ooh, I hit the wrong button. Yeah, I think. Oh no, that's alright, so that's bullshit. Next and previous. Thanks a lot. Alright, anyway. So we'll call that a video. It's abbreviated and such. The other video, like I said, it was just too boring. There's just nothing to argue. And my mouse has ceased to function. Alright. Needs a recharge. Desperately. See if it'll work on here. Yeah, it's much better. Alright, anyway, until the next time, and such and so forth, and whatnot.